Okay, so hi everybody. So the YouTube link is this. And actually, I just realized that I think if you just click in the top left corner, it shows you the YouTube links. So maybe I don't have to keep. Okay, so I'm gonna try writing on my laptop again. I don't think it's gonna crash, but actually, I'm just gonna keep writing on the tablet. It's fine. So it's lecture 19. And since we've covered a lot of concepts in the last two lectures, I'm just going to start by showing you this list of all the key definitions that we've been through. So here are the key. Here's the framework of probability that we've developed in the last two lectures. So behind every situation, there has to be an experiment which generates outcomes. And then the space of all outcomes is called the sample space, which is a set. And then you have a function on the set from the set to real numbers, which assigns probabilities to the outcomes. You have events that are subsets of the sample space. And then the probability of an event is just the sum of the probabilities of all the outcomes inside the event. So these first two lines are what we did in lecture 17. And then the most important thing which we've done, which we did in the last lecture, is this definition of conditional probability. This is probably the most subtle thing in probability theory, even though it's a simple formula. And when in doubt about anything regarding conditional probability, just use this formula. And then, okay, we stated the product rule, which is just a rearrangement of the definition of conditional probability. We stated the sum rule, which is it's just a restatement essentially of the formula for the size of the union of two sets that we covered quite a while back. Then I mentioned this law of total probability, which is just a combination of the sum rule and the definition of conditional probability. And we used this yesterday in our example where we talked about medical testing. And then there's this very important theorem called Bayes' theorem, which is actually just an immediate consequence of the product rule. But the key point is that it shows you how to compute the probability of E given F in terms of the probability of F given E. And finally, we defined the notion of independent events, which are events with the property of the probability of E and F. So the E intersection F is just the product of the probabilities. And we're going to talk a little bit more about that in this lecture. But before we move on, any questions about any of these definitions or concepts? Okay, so one important instructive example that we did last time to illustrate a lot of these concepts was this medical testing example, which I've just written here again. And here, okay, I won't review the whole example, but there was a disease and we had data that were estimates of the conditional probabilities of a positive test given that you have the disease and given that you don't have the disease. And we also had, importantly, we had an estimate of the number of people in the population who have the disease. So that's that's P of C here. C is the event that a random person from the population had cancer in this case. We're interested in the sort of relevant question to an individual taking this test, which is, what's the chance of testing positive? And if I test positive, what's the likelihood that I have the disease? And one important feature of this, so we did a calculation, we figured these things out. Here we just used the law of total probability to figure out the probability of testing positive. And then we use Bayes' rule to figure out the probability of having prostate cancer in this case, given that you tested positive. There's one feature of this which I really want to highlight, which is that we could not have done these calculations without knowing what fraction of the population actually had the disease. So we couldn't have done these calculations without knowing item 3, right? So this 0.116, this appeared in a very important way in both these calculations, right? So I want to point this out because in a lot of the current discussion surrounding COVID testing, people just talk about the rate of false positives or false negatives. That, you know, this test has so-and-so accuracy or sensitivity, or I forget what the other word that's used is. But the point I want to make is it's actually impossible to know. It's impossible to answer this question of, if I have a positive test, what's the likelihood that I have the disease, without knowing a third piece of information, which is what fraction of the population actually has the disease. And so this is something to keep in mind whenever you're interpreting any such testing results, but it's also a non-intuitive feature, right? It sounds like that if you know, if you just know what the probability of the test succeeding is, given in the two different cases, that should be enough to flip the conditioning, but it's not true. You need this third piece of information. And this is the source of a lot of the current confusion surrounding COVID testing. Okay, so any comments or questions about this? Okay, so I'm just going to add some pages. Okay, so what do I want to do in this lecture? I want to say a bit more about independence. And then I want to introduce a new concept, which is a concept of a random variable. And then I want to talk about some properties of this, of random variables. Most importantly, I want to talk about linearity of expectation. So let me say a little bit more about independence. So I want to do one more example. So what's the experiment? The experiment is going to be that I flip 3 coins. So flip 3 independent fair coins. So each coin can be heads or tails, and fair means it's equally likely to be heads and equally likely to be tails. And I'm going to consider 2 events. So I'm going to consider the event H1. This is the event that the first coin is heads. So I'm going to do something that I'm not. So there is an underlying sample space S, which is all 3 tuples of H and T. And H1 is going to be the set of all outcomes such that the first coin is heads. So that's one event. Or yeah, let me just call this event E1, just to avoid confusion since H is already there. Okay. And another event I'm going to be interested in, E odd, is the event that an odd number of heads appear. Now, events are always sets. So subsets of the sample space. And so there are always sets of outcomes. So often actually, as you start doing, in the practice of probability theory, we often actually don't even write this as such that. We just write it this way. And it's implicit that there's a S such that here. Okay, so these are two events. And independence has already appeared once. I've used it as a hypothesis or definition, right? So I've used it as a hypothesis, or you could call it an assumption or a definition in defining the experiment. So I've used this concept of independence to say that there's no, to specify that the probability, that the probability of a particular configuration of coins is just a product of the probabilities you get for the individual coins. So now I want to ask one question, which is, are these events independent? So before we try to investigate this, anyone have thoughts? Just
first, like calculate calculate the probability of E intersection F, and we do it in like two different ways and see if it's like the product of the probability of E and the probability of E odd.
That's a great answer. So your answer is, well, we don't know. Independent is a well-defined thing. Independent means exactly one thing. It means that the product of the intersection is the product of the probabilities of the events. So the reason I ask this is that if you just think about this intuitively, it seems like they might be dependent, right? Because both events involve the first coin. This is not like asking, oh, is the probability of the first coin heads independent of is the event that the first coin is heads independent of the event that the second coin is heads? That's kind of obvious that they're independent because they have nothing to do with each other. Or it lines up with our intuitive notion of independence. In this case, it's not so clear, right? Because both of these events involve the first coin. And so how do we find out? Well, we compute, we follow the definition. So, well, okay, what's the probability of E1? Well, it's the probability that the first coin is heads. And so that's a half. It has nothing to do with the other coins. What's the probability that you have an odd number of heads? Well, we could write out the whole sample space and just count them, but let's try to use some of the tools we've developed. So let's try to break this down into events that we have an easier chance that should be easier to compute. Any ideas about how to break up E odd?
Could we write out to see if like it's independent? We could say set it equal to P odd, E odd given E1.
Yeah, so we will eventually do that too, but first we have to know what PE odd is, right?
Mm-hmm.
So I'm just asking, like, to compute E odd, any thoughts on how to, I mean, of course you could write out the whole sample space, but any thoughts on how to break this into simpler events?
Would it be E1? Oh wait, no, sorry.
I think you could count the number of ways to get one head and the number of ways to get 3 heads.
Yeah. So you observe that E odd is a union of 2 events, which I'll call, okay, this is actually not such a good notation. Let's give these different letters. Let's call this F1 and F3, where F1 is, or I don't need to define new letters. Let's just do it like this. This is equal to the probability that you have exactly one head, and the probability plus the probability that you have exactly 3 heads. And what rule am I using here? I'm using the sum rule. So these are disjoint events, right? And now, okay, so now I can, I mean, okay, now it's pretty good. So exactly one head. How many ways are there to get exactly one head? Well, you choose which coin is heads, and then the other 2 are tails. And then the total number of configurations is 8. So it's 3 8s. And how many ways are there to get exactly 3 heads? Well, there's only one way. So the answer is 4/8, which is a half. Okay. Any questions about that computation? So here I use the sum rule.
Why is it over 8 again?
Well, so here it's because the size of the sample space is 2 to the 3, right? Because there are 2 options and 3 coins, so it's 8.
Thank you.
Yep. Okay, so now to check that whether they're independent, I have to check the probability of the intersection. Or rather, we could do it 2 ways, but yeah, no, let's just do it this way. So probability of E1 and E odd. So this is well, there are a number of ways to do this. You could say, we could use the product rule to say this is the probability of E odd given E1 times the probability of E1. Which is well, let's see. So there are a number of ways to do it. Do I want to do it this way? Yeah, sure, why not? So
Can we use the sum rule to get there pretty quick? Like it feels like we can do the same break we did above.
Good idea. Good
and
idea.
then notice that since we have E1, there's only one case for example.
Good idea. Good idea. Let's use the sum rule. So this is saying that this is the probability that the first coin is heads, and either you have exactly 1 head or 3. So again, by the sum rule, this will be the probability that E1 is heads and exactly 1 head, plus the probability that E1 is heads, or I guess, sorry, E1 is already the event that E1 is heads. So this is just E1. So, okay, I guess I should be using cleaner notation. So E1 and intersect the event that there's 1 head, plus E1 intersect the event that there are 3 heads. Yeah, so again, you're right. This is even easier. So probability that the first coin is a head and there's exactly 1 head, well, there's only one configuration that has that property, right? That's head, tail, tail. So there's a 1/8 probability of that happening. And what's the probability that the first coin is head and all 3 are heads? Well, then all 3 of them are heads. So it's 1/8 plus 1/8. So the answer is 1/4. So just to label these, this corresponds to the configuration head, tail, tail. This corresponds to the configuration head, head, head. And so the conclusion is that we have these numbers, and indeed, this satisfies the definition of independence, right? So this equals probability of E1 times probability of E odd. So these events are independent. Okay, so independence the same definition was used, but it appeared in two different ways. Initially, it was used as an assumption to define the experiment. Right? It's a rule specifying what the probability of the outcomes is. It's a product of the probabilities for each coin. And here, again, it appears, but here it appears as a conclusion. Or in a way, the independence was, it was a hidden independence here, right? It wasn't obvious. And this is really the art of probability theory often is finding these hidden independence and structures of conditional independence. So any questions or comments about this example?
Why did we calculate the third intersection, the P of E1 and P of E odd?
Because we wanted to ask if E1 and E odd are independent. And what's the definition of independence? Well, it requires computing this intersection.
Okay, thank you.
Yep. So intersection just means and, right? Probability of E happening and F happening. So, another way to interpret this is, what's the conceptual interpretation? It's saying whether or not you have an odd number of coins, the probability doesn't change if you know whether the first coin is heads or tails. And similarly, the probability of the first coin being heads or tails doesn't change if you happen to know that the number of heads is exactly 1. That's what this is. That's what this formula is saying, which is a kind of interesting fact. Any more questions about this?
There's a couple of like variations on this definition that you can derive pretty easily, right? Like P of E given F is equal to P of E.
Yeah, correct.
In a proof, would it be acceptable to use one of those definitions without justification?
Absolutely, yeah. So here's an alternate way to do this. So which somebody already suggested. So here's an alternate. The alternate way is, well, we computed P of E odd. Let's compute P of E odd given E1. So what that means is we've now, okay, so there are a couple of ways to go about this. One is you could use the definition of conditional independence, which I advise you to do at this stage since it's a new concept. Or you could use the conceptual meaning of conditional independence, which is there used to be this whole sample space. So sorry, I want to do it systematically. It used to be this whole, so we started off with this whole sample space. So there's the H part of the sample space, and there's a part of this is E1, right? The first coin is heads. And then there's the rest of the sample space. Sorry. And remember, what does conditioning mean? It means that you're taking this event to be your new sample space. So you're defining a new experiment. In which you zoomed in on this part of the sample space. And so if you're following this conceptual path, well, then what's the probability that you have E odd? Well, so the first coin is it's H because you've conditioned on E1, right? So you know you're an event E1. And so within that part of the sample space, how many points have an odd number of heads? Well, the first one has an odd number of heads, and the last one does. So this probability is 2/4, which is a half. And that equals probability of E odd, which we calculated earlier, so they're independent. Now this is you gotta really be confident about what you're doing if you want to do it this way. But this is ultimately what later on in life probabilists do. That if you condition on some event that you know is independent, you kind of implicitly are working in this other probability space. But here it's a little bit tricky because we're trying to prove that they're independent. So I don't. I prefer the first method. Yeah. Okay. Any more questions about this? Okay, so I want to make one comment about, so independence is really, really important. It's very important to know when events are independent. So let me tell you about a famous legal case that took place in England in the 90s. So this is the Sally Clark case, which is quite tragic, actually. So Sally Clark was a nurse in England who had 2 children. So child 1 was born in 1996 and died a few weeks after they were born. And then child 2 was born in 1997 and also died, which is a terrible tragedy. I can't imagine. And these children died of, there's a name for this, it's called SID, sudden infant death syndrome. And the medical data suggested that this happens in 1/8,500, a fraction of the population, which is actually seems kind of high. So now what happened to this woman was the prosecution made the case that the probability of 2 children dying it should be 1/8,500. That's the probability of the first child dying times the probability of the second child dying, which is 1 in 73 million. And this was accepted in the court, and the verdict was that she was guilty and she was put in jail. Now, I mean, on top of all of this stuff that happened to her, she spent a few years in jail. And then in 2001, the Royal Statistical Society said that these events are not independent, and they're not. So this has some genetic basis. So these events are not independent. And they did, I don't know how they calculated what the conditional probabilities were, but ultimately they concluded that the probability of this happening to her was not that low at all. Of C1 and C2 is actually, something much higher, like 1 in the maybe tens of thousands. I mean, I don't know how they got these numbers, but let's just say it's much higher. And as a result, she was released from jail. It was a mistrial. So, I mean, this is an extreme case, a very common type of mistake in applications of probability, which is assuming things are independent when they're not. And it has like really major consequences, both mathematically and also in applications. Okay, so any comments or questions about that? Okay, one more thing. So in the last lecture, one of you asked that can we revisit the Monty Hall problem? using these more sophisticated concepts. So roughly, okay, roughly what's happening? Well, we started off by doing probability theory where we write down every point in the sample space every time, and then we just do counting. Now we're doing more sophisticated things. Using these laws, we can compute probabilities without just enumerating everything. And so the question was, can you revisit Monty Hall using these more advanced concepts? And the answer is you can, and it's on the homework. And there's a guided set of steps for how to do it. So, yeah.
I was wondering with this word. So with the setup of the problem, then this wasn't addressed on the homework. We set it up, we say like the conditional or the probabilities for these various events are this, and this. The one thing that I was wondering is there any way to really quickly show that this is like a probability space without calculating the I guess I was slightly like intuitively it makes perfect sense that all the probabilities of each individual event or each individual outcome would sum to 1. But I'm wondering how you could quickly show that.
You mean just that the total probability is 1?
Yeah. You do like a layered summation?
You mean if you wanted to, you mean in the tree diagram we drew last time? Yeah, it would be an iterated summation. Yeah. So
Cool.
Yeah, that's how you would do it if you wanted to prove that. So we're kind of implicitly doing that here, right? Even in this example. So for each coin, it has its own little probability space where it just has a half of being heads and half of being tails.
Thank you.
Now we're defining in this bigger space, we have, the one that's drawn in this picture here, we have 8 points, and each of them has 1/8. And magically they all add up to 1. Well, it's not actually so magical. If you write out the summations, this always happens when you add independent random variables to a probability space, the probability still stays 1. It's a good question. Yeah. Okay, so now we're going to do a new thing, which is very important, which is random variables. So far, we've been talking about events. And events either happen or they don't. But often we're interested in outcomes, or we're interested in outcomes of experiments that don't just have a binary value, that have a numerical value. So, for example, let's look at this 3 coin flipping example again, but now with a slight twist. So the second example is going to be that I flip 3 independent biased coins, which each have a probability of being heads equal to some number q, where q is a number between 0 and 1. So there's some parameter in this problem. May not be a 1/2. Okay. And so the question we want to answer is, what's the average number of heads? So, okay, we now we haven't really defined what that means. Actually, there is only one natural way, which is you go over all the outcomes, you look at the number of heads, and then you average them, but according to some weights, according to the probabilities. And in order to reason about this, we introduced this new concept of a random variable. So let me define this. So a random variable on a probability space. So on a, yeah. So that means there's an underlying sample space, S, and a probability function P. So a random variable, the terminology is initially confusing because it's not a variable in the way that you've looked at it earlier, and it's actually not random. It's actually a function. X, we use capital letters usually to denote these, from the sample space to real numbers. So let's look in the above example, let's define a random variable to help answer a question. So in example 3, define X of S to be. So what are we interested in here? We're interested in the number of heads, right? So S is a point in the sample space. So okay, so let's actually explicitly write down the sample space. So in the example, what's the probability space? So sample space is again heads and tails. 3 of them. The probabilities are now more interesting. The probability of a particular outcome is, well, the probability of heads is Q. So it's Q to the number of heads times 1 minus Q raised to the number of tails. This is a slight twist from what we did earlier. But this P is a function on the sample space. And why am I multiplying these numbers together?
Because they are independent. Each flip is an independent event.
Yeah.
And we're talking about like an and relationship.
Exactly. So these are independent coins. So this is why this is the correct probability. And let's draw. And okay, so let's draw a picture of the sample space again. Actually, let me just copy it. I don't want to write all that stuff again. So we drew this, it's the same one. Except I guess we don't have this, we don't particularly care about this event E1 anymore. So this is the sample space. That's S. And now the random variable I'm going to define is a function from S to the real numbers. So this is a random variable. Where what's it going to do? Well, it's going to take a sample point and it's going to count the number of heads. So in this cartoon picture here, remember, a function is a rule that maps every element of the domain to an element of the codomain. So the codomain in this case is going to be the real numbers. And what's now going to happen is each point in the sample space is going to get mapped to a number, which is the number of heads, which can be 0, 1, 2, or 3 in this particular case. So this HHH is going to get mapped to, I guess, 3. TTT is going to get mapped to 0. And then let's see, what are the ones with one head? So with one head, there's some ugly looking set here. Maybe I should have written it a slightly different way, but let me just highlight these. The green ones are the ones with one head. So that's this, this, and this. These green ones are going to get mapped to here. And the ones with 2 heads, which are the remaining ones, the yellow ones, are going to get mapped to 2. So that's the function. Okay. Now, okay, what do we do with random variables? This is an important definition. Well, we compute averages of them, as we are going to do in this example. So let's put the second definition. The expectation of a random variable is, use this block E, Blackboard E notation, EX, is the sum over all points in the sample space of the probability of that point times the value of the function at that point. So it's just a weighted average, weighted by the probabilities. And the meaning is it's the average value, right? So this is just a weighted average of X with respect to the probabilities. So let's figure out what it is in this case. So in example 3, maybe let me move this down so I have more space to do it. Okay. So in this example above, we have that the expectation of X, well, it's a sum over 8 things, right? Because there are 8 points in the sample space. Okay, so this is kind of annoying. I don't want to write 8 terms with this algebraic expression. So any ideas on how to write it a little more efficiently? Just given this picture, anybody?
Good group by output.
Yeah, group by output, right? So in the definition, the terms are grouped, are not grouped. I mean, the terms are arranged according to input. But when you're actually computing the sum, you could group them by output, right? So what do you get? Well, you get 0 times the probability of TTT, or of getting, I guess literally, you get little p, sorry. So capital P is only for events, which are subsets. You get plus, now 1 is the green terms, and there are 3 of those. So you have 3 of those, and they all have the same probability. The reason this grouping makes sense is that the probability only depends on the number of heads. It doesn't depend on where they are. So here you get Q times 1 minus Q squared. These are the green terms. And now you look at the yellow terms. There are again, and so now there are three components, right? What is the value of the random variable? Well, that's 2, because there are 2 heads. Then how many terms are there? Well, there are 3. And then what's the probability? Well, the probability is Q squared times 1 minus Q. These are the yellow terms. And then finally, there is 1 which has a 3. There's only 1 term, and the probability of it is, oh, have I got this backwards? No, I have got this correct. Yeah, Q cubed. Okay, so that's what the average. So yeah, so I guess TTT we should just say is the probability of all of is 1 minus Q cubed. Okay, so that's the answer. Okay, maybe in the numerical example I should have set Q to be equal to something. So I don't know. Should we just do that? Let's just do that. Let's set. You know what? Do I really want to do all this arithmetic? Fine, let's do it. So let's set Q equal to 1/3. And then the algebra is good because it kind of shows you how the terms are grouped. So 0 term doesn't do anything. You get 3 times 1/3 times 4/9 plus 2 times 3 times 1/9 times 2/3 plus 3 times 1/27, which is, I don't know, what is that? So it's 12 plus 6. 12 plus 12 plus 1. So 25/27. So the average number of heads is less than 1. It's that number. Okay, makes sense since the probability of one of them being head was less than 1/2, but that happens to be what it is. So any questions about that computation?
A quick question, Professor.
Mhm.
So the random variable is still a probability value, so therefore it has to be in between 0 and 1, correct?
No. So
No?
the random variable is a function from x to reals, and it, as you can see, sometimes it takes value 3.
Okay.
So,
got it.
okay, just to look at another extreme example.
Mhm.
Suppose Q was 1. Then what is the expectation of x? So Q equals 1 means that the probability of each coin being heads is 1. So what's the outcome going to be in that case?
Oh, would it be like, I think it would be 3 if I'm doing
Yeah,
my
it would be
arithmetic
3.
correctly.
Because if Q was 1, then all the probabilities would be 0 except for the one corresponding to x equals 3. So then the average would be 3. So it's a great question, but expectations of random variables can be anything. They don't
Got
have to
it.
be 0 and 1.
Thank you.
Isn't the answer 1, not 25/27?
Have I done some wrong arithmetic? Oh, I absolutely have. Sorry. And yeah, there's another reason why the answer is 1, which we'll see in a moment. So the answer is 1. Sorry. I'll show you why the answer is 1 in a different way in a moment. I made an arithmetic mistake. It's 12 plus, the answer is 12 plus 12 Oh, no. 12 plus 12 plus 3. Ah, that's 27. Okay, sorry. Okay, fine. Thank you. The answer is 1. Which is less than 1.5, which is what you might think it would be if they're even. But, okay, sorry for that mistake. Okay, now, why did I do this example? Well, the definition of expectation is this, but in practice, there's an equivalent definition. So in the definition, what you do is you take a sum over the domain. You take a sum over the outcomes. So here in the first definition, this is a sum over outcomes, or sum over the domain of S, domain of X, right? Which is S. But in practice and in most cases, what you really do is you group the terms by the value that the random variable takes, right? Like in this example, we didn't add up 8 terms. We grouped the terms depending on what values the random variable took, namely 0, 1, 2, and 3. And then we multiplied each one by the probability that the random variable is equal to that value. Right? Like what's really going on here is, this number, this is the probability that X of S is equal to 0. This number here, this whole thing, including the 3, this is the probability that X of S is equal to 1. So if you group the terms according to the value in the codomain, or in the range of X, let's say, then you get another equivalent formulation. So by grouping terms according to the value of X of S. So this is different from grouping according to S. Here you group according to the value in the codomain. You get that the expectation of X is equal to the sum over all little r in the range of this function X in the way that we defined in chapter 2 of the value of the function, which is R, times the probability that X equals R. So there's an equivalent, often more useful definition. The first definition is also useful for some theoretical purposes, which I'll point out in a moment. So it's the same thing. If you just group the terms differently, you get this. And there's a slight new notation here. I'm using this notation. This is shorthand for the probability of, remember, so probability is only defined for events, right? So this is really the probability of the event S, so that X of S, or we've stopped writing the S even. So it's just the probability of the event that X of S equals R. So if I were to draw a cartoon of this, what's going on is, I have the domain S, I have the range, the real numbers, and I can partition this depending on the values that X takes, right? This is the set X equals 0, this is the set X equals 1, this is the set X equals 2, and so on. And these get mapped to some values, right? 0, 1, 2, etc. And so all I'm doing is I'm saying, hey, if I want to calculate the average of this function, what I can do instead is sum over the values in the range, and then just for each of them multiply them by the probability of the pre-image, of the inverse image. So I mean, yeah, to be even more, just to be in the same notation as chapter 2, let me write it as a inverse image, which I know is a sore subject for some people after the midterm. But so this is, sorry, not F, X inverse. of 0. This is X inverse. Sorry. Of 1, etc. Okay. So any questions about this equivalent definition of expectation? So in the first definition, you sum over the domain. In the second expectation, you arrange it as a sum over the codomain, over the range. Okay. So now let me generalize this example. So this example 3 that we did comes up a lot. It comes up all over math, science, statistics, social science. This comes up a lot, that you have a bunch of independent coins that all have the same bias. So this is, let me just abstract this. So generalization is something called Bernoulli trials. So the experiment is you flip n independent bias coins, each with probability of being head equal to Q, and probability of being tail equal to 1 minus Q. And so now, in general, let's calculate the expected number of heads. So let X be the number of heads. So this is a real number. It's actually an integer. It takes values between 0 and n. Which is a valid, for our definition, because that's a subset of the real numbers. So, I mean, okay, this doesn't need to be really written, but it is. And so now let's try to, so now in this situation, we would be kind of in trouble. I mean, it would be annoying to do the first definition, because how many points are there in the sample space?
To the end.
To the end, there are a lot of points. You don't want to write all those points, right? And the probability of a particular outcome is again Q to the number of heads times 1 minus Q to the number of tails. So that's a full description of the probability distribution. And now let's study this random variable. Let's use the second definition to compute its expectation. So for the second definition, you now need to compute the probabilities that the random variable is equal to R for different values of R. So let's compute the probability that the random variable is equal to K. Well, this is now a counting problem. So how many bit strings are there with exactly K heads? Well, n choose K. And once you choose the positions of the heads, the probability of that particular outcome is going to be Q to the number of heads times 1 minus Q to the number of tails, which is n minus K. So just to rearrange, this is the number of, number of positions, or number of, the number of arrangements, okay, you know what I mean. It's the number of ways to put K, to have a string with K H's and n minus K T's. But this is different from counting, because the bias of the coin now introduces the second term. This is the probability of any particular arrangement. with k h's. This is the probability of any particular outcome. The probability of particular arrangement, let's say. So any questions about this calculation? So by the way, we did this little calculation, and as Ben was asking earlier, it seems that the probabilities magically always add up to 1. Why do the probabilities add up to 1 in this case? Can anybody see? Anybody?
If we take the summation, we just have the binomial formula.
Yeah. So if you add up all of these, so k can go from 0 to n of these probabilities, then you just get the binomial theorem. Okay, so good sanity check. Because after all, the random variable always has some value. And so the sum of these things had better be equal to 1. Because these events exhaust the space. Okay, so now let's calculate the expected value. Well, it's the sum over all outcomes, which in this case are these values k going from 0 to n, times the value of the outcome, which is just k, times the probability, which is n choose k, q to the k, 1 minus q to the k. That's a pretty ugly looking formula. You can do some hacking around to simplify it. So you can open the factorials. And then, okay, you get to cancel some k here, and then this becomes k minus 1 factorial. And then, okay, then you can do this sort of cheap trick where you can pull out an n. You can make this n times n minus 1 factorial. Maybe I shouldn't have crossed it out, but okay. And now you can kind of squint and see that this is actually q times n times summation k goes from 0 to n of n minus 1 factorial over n minus 1 minus oh, wait a minute. No, sorry. Well, okay, I'm balking a little bit because what is k minus 1 factorial when k is 0? That's not so great, right? So,
But we can just drop the k equals 0 case, because when k is equal to 0, this whole thing works out to be 0, like the top
yeah,
line.
that's right. So when k is 0, this whole thing is 0, so we can just start at k equals 1. Okay, so we go from k equals 1 to n. You get n minus 1 minus, sorry. Minus k minus 1 factorial times k minus 1 factorial, q to the k minus 1, 1 minus q, sorry, this is n minus k. And now you have n minus 1 minus k minus 1. And this is another copy of the binomial theorem. So all this stuff is just 1. So you get qn. So that's a tricky conversation. That's a tricky calculation. But in the end, you get kind of what you expect, that if each coin is heads a q fraction of the time, then a q fraction of the average number of coins that are heads is a q fraction of the total number. So not conceptually surprising, but a bit of an annoying computation. Any questions about this computation? It's not very important because I'm just about to show you an infinitely better way to do this computation. Okay, so this is a kind of silly way to do this computation. There's a much better way based on this extremely deep, I mean, not deep, extremely easy, but very, very, very useful property of expectation, which is called linearity of expectation. So I use this all the time in my research, and so does everybody. It's really a very powerful thing. So let me tell you what it is. So first, let's say what it means to define to add two random variables. So you can add two random variables. X1. They need to be on the same space. By defining a new random variable, which is the sum, to just be the sum of the evaluations of the original one. This looks like nothing happened here, but I'm actually doing something. I'm defining a new function by adding two functions. And for people who took Math 54, the space of random variables is actually a vector space. But if you didn't, then don't worry about that. You can add random variables. You can multiply them by scalars as well in the obvious way. So linearity of expectation is the following very important property. It says if x1 and x2 are random variables on the same probability space, the same sample space, then the expectation of x1 plus x2 is the expectation of x1 plus the expectation of x2. So in words, what this is saying is that the average of the sum is the sum of the averages. The proof is really immediate from the first definition of expectation, where you sum over the sample space. So let's see that. Well, expectation of x1 plus x2 is the sum over the sample space of the probability of the outcome times x1 plus x2 of this point. But by the definition, that's just you can distribute this, right? And now you again distribute this across the summation. You just get two sums. And that's the sum of the expectations. Okay, so it's very easy to prove with the first definition. Not so easy to prove using the second one. I mean, it's not hard, but it's a little more annoying. Now, this is a very beautiful thing that can be used to solve many questions much more easily. So let's revisit our Bernoulli Trials example. Well, so remember, X is the number of heads, right? That was our original random variable. What I'm going to do is I'm going to define some new random variables. Define xi to be 1 if the ith coin is heads, and 0 if it's tails. For I goes from 1 to their n coins, right? So there are these n coins, right? And what I've done is I've defined a random variable for each coin, which tells me, which is just a very simple one. It tells me, it says 1 if the coin is heads and 0 otherwise. This is called an indicator random variable. That's the jargon. It's not really a new concept, but that's what it's called. It's called an indicator. A 0-1 random variable. Because it tells us if something happened. So now the nice thing is, what's the expectation of one of these xi's? So what's the expectation of x1? Well, this only depends on the first coin. So it's 0 times the probability that x1 is 0 plus 1 times the probability that x1 is 1. So the 0 term doesn't matter since it gets multiplied by 0. And what's the probability that x1 is 1?
That would be Q, right?
Q, because the probability of each coin being head is 1. So the expectation of this is just Q. And in general, expectation of xi, so for every I, expectation of xi is also Q for the same reason. So by linearity, well, okay, there's one more assumption, right? I mean, there's one more fact also. So also, the thing I'm interested in, the total number of heads, how is it related to the xi?
It's the sum of all the xi.
It's a sum. Yeah, you get a 1 for every head. So it's x1 plus x2 all the way up to xn. So by linearity, you get that expectation of x is equal to expectation of the sum of the xi's, which by linearity is the sum of the expectation of the xi's, which is just, each one is q, so it's just q times n. So this is way easier. It allowed you to study this whole system by studying one coin at a time. Any questions about that?
I have a question about seeing random variables as a vector space. It seems like we could create similar vector spaces by mapping not just to R, but to like other vector spaces, like the set of polynomials or something. Is that ever done?
Yeah, it's definitely done.
Cool.
Yeah. Well, you need to be able to multiply whatever the codomain is by real numbers. Otherwise, you're going to have trouble, right?
Yeah, which is why it has to be a vector space.
Okay, let's do one more example, and then I'll continue next time with more about random variables. I don't know what number we're on for. So suppose pi is a random permutation of 1 through n. So what's the average number of fixed points? Now, if you really wanted to do this, it would be, I mean, there are a number of ways to do it, but some of the ways are kind of hard. If you literally went through the sample space, computed the probability of every possible number of fixed points, and then averaged them, you would get the answer. That's correct. So here the random variable is x. So S is now the set of all permutations, right? And the distribution P is just uniform. So X is now a function from S to real numbers, where X of a permutation is the number of fixed points. So this would come up if, for example, I just gave everybody back, you know, we graded all the exams and then gave them all to random people in the class instead of to who they were assigned. The question is how many people would get back their exam on average. Now, again, using linearity, this can be solved very simply. The creativity is, how do you break down this complicated random variable into simpler ones? And so the idea is, well, define a random variable that only looks at a small piece of the outcome at a time. So define xi to be the indicator random variable of 1 if pi I equals I, and 0 if pi I does not equal I. So if I is a fixed point. So this only looks at what happens to I. That's why it's a simple random variable. Now observe that the expectation of x is the expectation of the sum of these xi's, right? Because the total number of fixed points is the sum of the, for each one I get a 1 if that thing is a fixed point. And by linearity, that's just the sum of the expectations, right? So I use linearity in the last step. So now this is nice because all I need to do is compute the expectation of one of these things, and that's easy. So the expectation of xi is just, well, it's just the probability that I is a fixed point. It's 1 times that, right? Plus 0. And what's the probability that I is a fixed point? For some fixed I.
1/26. Or 1/n.
Well, somebody said 1/n. Yeah. Now, there are a number of ways of thinking about this. The most concrete is to just do counting. You want to count permutations that map I to I. Well, there are n minus 1 factorial of those, and there are n factorial total permutations. So the answer is 1/n. Right? So this numerator is permutations that fix I. So then what's the conclusion? Well, the average number of permutations is just, this is the same for every I, so it's just n times 1/n. So it's just 1. So this is a beautiful fact. It doesn't depend on n. No matter how big the permutation is, no matter how big the class is, and you do this random allocation, on average, 1 person will get back their exam. And this is very easy, and this is not easy to do without linearity of expectation. Any questions?
Where you wrote observe, you wrote expectation of x equals expectation of the sum of x1 all the way to xn.
Yeah.
What does the left-hand side of that mean? Like expectation of x?
Oh, so x is a random variable. And expectation of X is, just the thing we've been talking about. Like you define expectation of a random variable, this. So all we're saying is that we wanted to compute the average number of fixed points that corresponds to the expectation of X, where X is this random variable. It is the number of fixed points of, number of fixed points of pi, right?
Okay, thank you.
Yeah. So really the fact we're using is that X is equal to the sum of the xi's. Right? The total number of fixed points, it's the same as saying, well, I get a 1 point for each fixed point, and then I add up all those points. Any other questions or comments? Okay, well, that's it for today. So I guess see you next time.
Awesome. Thank you.
Yep, thanks.
Thank you.